Welcome back to the Foundry by Forge College. So, in our last explainer, Foundations of Decentralization, we laid down the groundwork with decentralized ledgers, the basic memory of the blockchain. But today is where it gets really fun. We're diving into smart contracts and application models. We're basically stepping out of a world that just records simple transactions and right into a universe of fully programmable applications. It's time to see what makes Web3 actually tick.
Here's our blueprint for today's explainer. We're going to hit the programmable blockchain layer, jump into the mechanics of smart contracts, look at some real-world Web3 applications, dissect the anatomy of an escrow, and then wrap it all up with key takeaways and next steps.
All right, Section 1, the programmable blockchain layer. Let's see how we upgrade this ledger.
Think about your typical everyday agreement. It relies heavily on off-chain human promises. Like, when your friend loosely promises to pay you back for lunch next week and then magically develops amnesia. Yeah, there's a lot of room for interpretation, delays, and just human error. On-chain contracts completely flip this script. They rely on deterministic, automated enforcement. So unlike your friend, a smart contract literally forces the transaction to execute the exact millisecond its conditions are met. There's zero negotiating, no excuses, and definitely no amnesia.
The absolute crucial takeaway here is that smart contracts replace human mediators with raw code. By definition, they are deterministic, on-chain programs paired with a persistent state, and they update automatically when triggered by transactions. Now, if you're wondering what deterministic means in this context, it just means that if you give the contract the exact same inputs, it is going to produce the exact same outputs every single time, across every single node on the network. A transaction comes in, triggers the contract, it wakes up, runs its logic, and updates the network state completely automatically.
Moving on to Section 2, mechanics of smart contracts. Let's look under the hood.
Okay, so here are the 5 main components making this whole system tick. You've got transactions, which act as the trigger based on user intent, contract storage, which is basically the long-term memory for identities and balances, the deterministic virtual machine is the engine actually running the code, then you have gas, which is the fuel, and events, which act as the output signals. But I really want you to notice the gas and metering row here. Gas acts as this incredibly strict economic toll booth. Think about it. Blockchains are running on thousands of computers globally. If some developer accidentally or maliciously writes an endless loop, it could literally crash the entire network, state. Gas prevents that. Since every single operation costs a tiny fee, a heavy, inefficient loop will just run out of gas, fail safely, and end up costing the developer their own money. It's an absolutely brilliant built-in anti-abuse mechanism. And that brings us to a golden rule of Web3 app design. When you're building, you always have to ask yourself, what needs to be locked away trustlessly in the on-chain vault, and what actually requires an external oracle to verify? The rule of thumb is that immutable records, like token balances and your core logic, belong securely in contract storage. But remember, blockchains are isolated by design. They can't just go online and check the real-world weather, or look up the current price of a stock. So that external verification belongs to off-chain tools called oracles. Basically, you keep all the messy, unpredictable real-world data outside and keep the absolute mathematical truths safely inside.
All right, Section 3, real-world Web3 applications. Let's see what we can actually build with this stuff.
Our first core application model is the token. Now, think of a token contract as an unbreakable digital spreadsheet. The code mathematically guarantees you can never, ever spend the same coin twice. It strictly enforces what we call invariance. That's just a fancy engineering term for a rule that absolutely cannot be broken. So when you send a token, the contract performs an atomic balance update, meaning it subtracts the amount from your account and adds it to mine at the exact same millisecond. It's all or nothing.
Next up, we have DAOs, or decentralized autonomous organizations. DAOs are fascinating because they take all that messy, slow human bureaucracy and map it into a precise on-chain voting process. And they do it without needing a central boss. It's usually a clean 3-step process. Step 1, someone submits a proposal directly to the contract. Step 2, a voting period opens up and securely records the votes using snapshots. And Step 3, if it gets approved, the contract automatically executes the code. No managers, no stuffy board meetings. Just pure, transparent, automated execution based entirely on community consensus. And then we have the escrow. I like to think of the smart contract escrow as the ultimate digital vending machine. It just stubbornly refuses to release your asset until the exact right conditions are mathematically proven. It holds the funds securely in its own isolated state, acting as a completely neutral party, just waiting for the trigger that proves the delivery conditions have been met.
Section 4. The anatomy of an escrow. Let's actually walk through some code.
So, right at the top of our escrow code, we have to define the contract's persistent memory. These are the state variables. We need to lock in exactly who is paying, who is receiving the funds, the exact amount of the deposit, and a simple true or false status for whether the job is paid or not. This effectively forms the indisputable ground truth reality that our contract is going to rely on.
Now, take a look at this require statement. I love this part because it acts as an uncompromising digital bouncer. It guarantees that only the payer can release the funds. Literally, if anyone else on the entire internet tries to trigger that release function, the contract throws an error saying only payer can confirm, and it just instantly kicks them out. The bouncer says no, and the transaction reverts.
When it is finally time to release the money, the order of operations is absolutely critical. Step 1. The contract verifies that the funds actually exist. But look really closely at Step 2 here. It updates its internal state to 0 before moving to Step 3, which is the external call to actually transfer the funds. Why? Well, to avoid devastating bugs like a reentrancy attack, which is where a hacker tricks the contract into paying out over and over again, the contract has to strictly update its own internal reality first. It makes its balance 0, and only then does it send the actual funds. It's a total lifesaver.
Once those funds safely leave, the contract shoots out an event. You can think of an event as a cheap flare shot up into the sky, just so off-chain interfaces know the deal is officially finalized. So it emits this released log, and that's how the front-end website you're looking at knows to suddenly update, flash a nice green checkmark, and let you know your transaction was a total success.
Let's head into Section 5, Key Takeaways and Next Steps.
Consider this your ultimate Web3 design checklist. First up, enforce your invariance trustlessly via on-chain code. If it has to be guaranteed, put it on-chain. Second, design efficiently for gas and resource metering. Don't write bloated code or it'll cost a fortune to run. Third, and I can't stress this enough, always update your state before making external calls. Protect yourself from those reentrancy exploits. And finally, use events as your observable side channel so off-chain observers know what's happening.
So, our digital vending machine works perfectly out there in the open public. But that leaves us with a pretty massive question for our next lesson. How do we actually add identity, privacy, and cross-chain capabilities to these very public application blueprints? Because let's face it, real-world applications usually need authorized actors, some level of off-chain privacy, and the ability to interact across completely different blockchains.
And that is exactly what we're going to tackle next time. Thank you so much for joining me for this explainer. To keep exploring these concepts, to solve those privacy and identity puzzles, and just really level up your Web3 knowledge, be sure to visit forge.college. Trust me, there is a lot more to learn. I'll see you in the next one.